Hello there. Today I'm going to be teaching an introduction to particles and radiation. First of all, we're going to start off with an electron, which has the symbol E-, a proton, which has a symbol P, and a neutron, which has a letter N. So, what are these? These are particles that make up an atom, with an electron being charged with a negative charge. Negative -1 is the charge of an electron. Then we've got a proton with a +1 charge and a neutron with a 0 charge. Right, as you probably know that from GCSE anyway. You've then got an electron. We know it has a -1 charge, but the actual charge, instead of using relative charge, we need to use the actual charge in coulombs, which is the unit for charge, and it's 1.6 times 10 to the -19 coulombs. Negative, because it's negative charge. Then we've got the proton. If the proton has a +1 charge, that must mean that we have a 1.6 times 10 to the -19 coulombs positive. Then the neutron just remains as 0 coulombs, right? So, as we know from the structure of the atom, we've got the nucleus, and then we've got the electron rings. The nucleus is where the neutrons and the protons are, and the electrons are in the outer shells. So, let's now move on to a more advanced topic. To introduce it, we can begin with antiparticles. Proton, neutron, electron. These are particles. Yep. For each one of these particles, however, we have a corresponding antiparticle. Therefore, we must have an antiproton, an antineutron, and for an electron, however, it's called the positron. And the reason it's different is because when the positron was discovered, we didn't know that it was actually the antiparticle of an electron. We just thought that it was a positively charged electron. So we called it a positron, not knowing that it was actually an antiparticle of an electron. But we now know that, and the name just stuck. So, proton, antiproton, they're separate particles. They have the equivalent mass, same. However, because in a system, mass, there we go, charge must always be conserved. Charge, opposite. Now obviously this doesn't take effect for a neutron and an antineutron because they have a charge of 0. But for a proton, we'll have a charge of 1.6 times 10 to the -19 coulombs. For an antiproton, we're going to have a charge of -1.6 times 10 to the -19 coulombs. As for an electron, the electron's going to have -1.6 times 10 to the -19 coulombs. The positron is going to have positive 1.6 times 10 to the minus 19 coulombs. So, with these particles and antiparticles, it's important we note that when an antiparticle meets its corresponding particle in space, when these two meet each other, you get something called annihilation. If I can spell. And what happens then is these particles come toward each other. Say we've got an electron and a positron. They come together, and as a result they collide, and because they're antiparticles of each other, you get annihilation, and they essentially cease to exist. Now, because we have the conservation of energy and the conservation of mass, through the equation E equals mc squared, we get 2 gamma photons as a result. And these 2 gamma photons will have the kinetic energy which is equivalent to the rest energy of these particles, right? And we can calculate the energy of these particles through we can calculate the energy of the photons through E equals hf. We can calculate the speed of photons through c equals f lambda. We can that's pretty much it for photons, really. I mean, you've got the other one, which is another one for energy, but let's focus on these 2 for now, where f is the frequency of the photon, lambda, which is this symbol here, is the wavelength of the photon, and c is given to us, which is 3 times 10 to the 8 meters per second. So that's the speed of light. We can also then work out the energy. We can work out the energy through E equals mc squared, where E is the rest energy, so we add a little naught to it, if you may, and then a little naught on the m as well, which means rest mass. So essentially, when we multiply the mass by speed squared, where speed is 3 times 10 to the 8 meters per second, we will end up with the energy of these 2 particles. And what we can then do with that energy is, if we've once calculated the combined mass of those times by 3 times 10 to the 8 meters per second, we'll then end up with energy of the combined particles that have been converted into energy from mass. Now, this energy, of course, has been given to us through this equation here as well, but we know that the sum of the energy of these 2 particles is then the energy of these 2. So if we divide that by 2, we'll get the energy of one of them, and then we can sub that in there, where we just calculated E. We now come into play with this h here, which is 6.63 times 10 to the minus 34, which is Planck's constant. We can then use E divided by h to calculate the frequency of the photons, if you may. But that just as an overall concept, is annihilation. And it occurs when we have an antiparticle colliding in space with its corresponding particle, or a particle colliding with its corresponding antiparticle, depending on how you want to say it. Now, there's a few more particles that we need to know through this introduction, and we have ourselves. I'm going to introduce it in a different way actually. I'm going to introduce it in a way where we have a neutron. This neutron can undergo something called decay, and it's going to undergo this decay via the weak force, but we don't need to know that yet. So neutron is going to decay via the weak force to a proton. Now, when we've got a neutron decaying into a proton, we have beta minus decay. That's the name of the decay. But as you know, their mass is not equivalent. Therefore, we need to apply conservation of mass. Therefore, the products that we get are a beta minus particle and an electron antineutrino. Now, essentially what this beta minus particle is it's just an electron. Don't really give the name a beta minus particle because it's emitted in the form of beta minus radiation is what's going on. Now this here, an electron antineutrino, it's an antiparticle of the electron neutrino, and it has no charge, zero charge, and it has a very, very minimal mass. Its mass is so small that it's basically negligible. But it is there, and we have to write it because we have conservation of mass and conservation of energy. Actually, it's one of the reasons why we have it. It's conservation of energy. Yeah, so that's beta minus decay. Now, there's another form of decay via the weak force, and it's where a proton decays into a neutron. Now, in this case, beta plus decay, we will have a proton decaying into a neutron, which we have a beta plus particle and an electron neutrino. Now, of course, this still has zero charge. However, it is the antiparticle to that. Now, these are very short-lived as well. Just want to add. So this here, it's not an electron this time. It's a positron because it's got a positive charge. Now, as I previously stated, a beta particle is an electron, right? So a beta minus particle is an electron because it's negatively charged. However, a beta plus particle is going to be a positively charged electron, as we know is the positron, which is the electron's antiparticle. So it's basically a positron, right? But it's emitted from the weak force decay as beta radiation, and that's what you need to know for that. And again, the reason we have these particles here, and it doesn't just decay like that, they have very similar masses, but they're not exactly the same. And the reason we have these particles and not larger particles is because they are so small, and the electron's mass compared to a baryon like a proton or a neutron is very, very, very small, and especially the electron neutrino basically has negligible mass. Let's get rid of this. And as I just mentioned then, we have something called a baryon. So let's just start off up here. We have something called hadron, and we have something called a lepton. So a lepton, our leptons that we have, is an electron. We also have a muon. Now, a muon is essentially a big electron. That's all we need to know. So we've got an electron and we've got a muon. Now, for hadrons, we have baryons and we have mesons. Now, baryons, the only baryons that we need to know are a neutron and a proton. Now, these have much larger masses than those. And for mesons, we need to know the pion and the kaon. Also the kaon. So pions, kaons, neutrons, protons, they're all hadrons, but as you can see, we have subclasses of a hadron. Yeah, it just is what it is. So we've got hadrons, we've got leptons. It's then, where can we go from there? We can start talking about conservation. So with baryons, we have something called a baryon number, and this number is always conserved. This number here is always conserved when we have an equation. So for example, when we just had beta minus decay, baryon number will be conserved because we have a baryon number of +1 for a neutron, and we have a baryon number of +1 for a proton on the other side. Therefore, they've been conserved. And just going back to conservation there, we can note that, therefore, if we have a baryon number of +1, it means we've either got one neutron or one proton, or we can also have, as we know, we can have an anti neutron, and we can also have an anti-proton. And essentially what's going on if we have that sort of situation, if we had annihilation between a neutron and an anti-neutron, say, or as we did last time, we had annihilation between a proton and an anti-proton. In that scenario, the proton will have a baryon number of +1, the anti-proton will have a baryon number of -1. Therefore, we have an overall baryon number of 0. And when we go to the other side of the equation, we had 2 photons, right? 2 gamma photons. And as you can see from there, there's no baryons on the other side. So we don't need to worry about that because conservation laws are successfully applied in that scenario. Therefore, it is something that can occur in space. Another thing that's conserved is lepton number. For example, if we had an electron, we'd have a lepton number of +1, but it's important to note as well that we have lepton electron numbers, and then we have lepton muon numbers. It can seem confusing at first, but it's just what it is. We've got conservation for electrons, and we've also got conservation for muons. So the amount of electron lepton number that we have at the start of the equation, we need to have the same amount of electron lepton number on the other side of the equation. We've then got a muon. if on the left hand side we've got a muon lepton number of 1, on the other hand side we need a muon lepton number of 1 as well. So that's just conservation. So if you go to your data sheet, you will be able to see. I don't have a data sheet. Never mind then. We've got quarks. Now quarks are fundamental particles. As we know, you may think that electrons, protons, neutrons, and now kaons, mesons, mesons, which are kaons, and pions. We know that you probably think that they're as small as we can get, but they're not, because we have quarks, and they're essentially what hadrons are made up of. Hadrons made of quarks. Hadrons are made of quarks, right? Now, if we go to baryons, so we've got proton and neutron. Proton, neutron. They are made up of 3 quarks. Now they're made up of 3 quarks each. If we, however, so that's baryon. Those are baryons. If we then go to mesons, which are the other type of hadron, we have ourselves a kaon and a pion. There will be more, but these are the ones that we're going to be focused on for the A level. They are going to be made up of only 2 quarks. Right, so I believe off the top of my head, a proton, without a data sheet, a proton is going to be made up of 2 up quarks and a down quark. So you know. And a neutron is going to be made up of an up quark and 2 down quarks. The reason behind this is because an up quark has a charge of 2/3, and down quark has a charge of -1/3. Therefore, 2/3 times 2 minus 1/3 is 1. Therefore, we get the relative charge of a proton. And for a neutron, we've got up, down, down. Therefore, 2/3 minus 2/3 is 0. So we've got 0 charge for a neutron. And that explains that. But we've got these 2 quarks here. We're missing out one more quark that we need to know. And that's the strange quark. Now, the main one here, the main strange particle that we're going to have is a kaon, which is a type of meson. Up here, this is strange. Now, I can't remember the exact strangeness now because I don't have my data sheet with me, but the kaon is strange. Now, what does this mean? It means that it basically does nothing for a long period of time. So it lasts for a lot longer, doesn't decay as quickly as some of the particles do, like through beta plus or beta minus. It's just there for a longer period of time. So we can write for our definition of strange. I mean, it's not really that important to note, but it's definitely, nice to know that the reason why kaon is strange is because they last long in space and they don't really do much. Yep. So now linking back, I'm going to explain a little more about quarks. Oh, and I just deleted the title. Quarks, that'll do us. Up, down, strange. So, actually let's just go for that. Let's just focus on the strange. A strange particle, a strange quark, has a strangeness of -1. Now that's just a property that we have. Now strangeness, strangeness doesn't have to be conserved. Strangeness doesn't have to be conserved in both the strong force and the weak force. I believe it's the strong force where it doesn't have to be conserved in the strong force. So in the one that it, so we've got the strong force, and we've got the weak force. So the strong force will produce strange particles. The weak force, however, will decay strange particles. So we've got another particle that's strange called the sigma particle, and that's going to have strangeness too. And they quite like to use that in questions on the exam papers, as well as the kaon. And of course, if we had an anti-strange particle, through conservation of strangeness there, we must have a strangeness of +1. Right? So, through the weak force, again, we decay strange particles. Through the strong force, we produce strange particles. Right. So on the one, there's one between the strong and the weak force, where the strangeness doesn't have to be conserved, and when the strangeness isn't conserved, when the strangeness is not conserved, we can alter it by up to 1, or plus or minus 1, essentially. So on one side, I'm pretty sure it's the strong force, but yeah, it must be the strong force because that's the one where we are producing the particles, the strange particles. We can only not conserve it by up to 1 more or up to 1 less. That's the that's sort of the conservation law for strangeness. I've now got the strong force, which we haven't really looked at that much so far. I've mentioned a few things to do with it, but what exactly is the strong force? So the strong force holds the nucleus together. So it holds the nucleus together, right? So we have protons and neutrons in the nucleus. But if we've got a positively charged nucleus, why doesn't the nucleus just implode? Well, that's because we have something called the strong force. Now, if I draw a graph for the strong force, we have attractive down here, and repulsive. There. So, I'm going to draw two little marks just for myself. And as you probably know, protons positively charged. They're going to want to move apart. They're going to want to repel each other. But what's stopping the nucleus from just imploding? Well, we've got the strong force here. And the thing about the strong force is, if we've got a force that's holding the nucleus together, well, if this force is able to overcome the electromagnetic force of the proton repulsion, then it would just come to a point. But that's where we have this point here, which is about 0.5 femtometers. And at that point, it's actually repulsive. And that sort of prevents the nucleus from just getting squished to a point. But then the strong force is also stopping it from just imploding, you know? So it's basically retaining the stability of the nucleus. As we come down here, it sort of looks like that, give or take, to the point where this here is 3 femtometers, this here is 0.5 centimeters. So you need to know those values really. It's around 3 to 4 femtometers when the strong force no longer has any effect on the nuclides, but it's at that point there, at 0.5 femtometers, where it is repulsive. So as it comes to 0.5 femtometers, if we have two protons and they are coming together via this attractive force, they are moving closer and closer together because of this attractive force. When it hits 0.5 femtometers, so when these are 0.5 femtometers apart, we will again repel until we're just sort of balancing around, and that's what retains the stability of the nucleus. Essentially overcoming the electromagnetic force. Now, something that we need to know as well is Feynman diagrams, but I just want to start off with something called an exchange particle. So, let me get rid of this. Exchange particle. So the exchange particle is essentially something that will carry the force between two particles in space in order to transfer momentum. So, or energy, essentially. So, for example, we have the strong force. And via the strong force, we have an exchange particle for the strong force. Which is the believe it's the pion. The new one. Let's leave that one up now. Weak force. as we've already discussed, via beta plus and beta minus decay, we have the weak force. And the weak force exchange particle that carries the momentum between, for example, a neutron to a proton, carries the energy across, is going to be a W boson. We've then got the electromagnetic force. For example, when we saw, if we, for example, had a electron and a positron come together, and or an electron and a proton, we have that electromagnetic force between the charges. They're going to want to come together, and that's exchanged via a virtual photon. It's exchanged via a virtual photon, and this has the symbol gamma because it's basically a gamma photon. And the reason it's virtual is because we can't see it, and the reason we can't see it is because if we use energy to see the photon, then we won't be able to see it. It gets confusing, but we don't need to know that. It's just virtual because we can't see it, because we can't physically see the photon, because that would put energy into the system, and so it's a virtual photon, and it's basically a gamma photon, or gamma radiation, whatever you want to call it. And of course we've got the strong force, which I very gave very small amount of attention to earlier, and I believe it's the pion is the exchange particle. It's a hadron. And we have a hadron as an exchange particle for the strong force, and I'm sure it's the pion. So we have the pion as the exchange particle, and the way we can think of an exchange particle and the purpose of an exchange particle is if we threw a ball towards another person, and this person threw the ball to the other person. The ball is basically the exchange particle, because it's the ball that's transferring momentum to them. So of course they will repel as well because conservation of momentum, but the ball goes that way, and he's using the ball to transfer the momentum, therefore transfer the energy to the person. And it works the same way, for example, the electromagnetic force, when we've got a proton and an electron come together. We're exchanging forces, we're exchanging energy, especially when we have coupling devices or coupling situations in mechanics. Just a little example of that. So when we have momentum, and we have objects that come together and their momentum together is the same as the total momentum before, and we can then use the mass total to calculate the new velocity of the combined objects. So that's basically what I meant by that. That's the first part of particles, I guess. Trying to think what else there is. I mean, I haven't really discussed Feynman diagrams. Let's discuss Feynman diagrams. Feynman diagrams. We have. Let's do beta minus decay. So we have. Good drawing these. We've got that. Got that. Got the proton. Got the neutron decaying into a proton. And then we've got ourselves. What have we got then? A minus particle and an electron and a neutrino. Because this is beta minus decay. Because we have, and actually this is a very good explanation of exchange particles here. We've got a neutron, and this neutron will have a it will have a charge of 0, and as we come up here we lose a charge, right, because we've gone from 0 charge to 1. Therefore we need to carry this charge across here, because then we can just basically call this, we're just basically calling this a negative charge, because we've lost the charge there, so we've just got to carry the charge going because conservation of charge. This then goes here, for which the negative charge goes into this. So we've then conserved charge. But it's this exchange particle here that sort of carries out the whole sort of exchanging of the particle interactions, forces and charge and all sorts really. So that's W minus boson. You can also have W plus bosons for carrying a positive charge. For example, if this was the other way around and we wanted proton, neutron decay, which is beta plus decay, we would have a positive boson, W plus boson. Yeah, that's that. We can also have a variety of different Feynman diagrams, but I'm not going to draw those all out. What else do we have? Let's have a look. Ah, there you go. Radiation. Radiation. Alpha. Alpha decay. We start off with an atom. Let's call it. No, let's not call it P because it's going to be proton. Let's call it. What should we call it? Let's just call it B. Let's just call it B. We have A. We have Z. This is then going to decay via alpha decay into A minus 4, Z minus 2. Let's just call it C because it's changed proton number, and when something changes proton number, it changes element, which you probably know. Plus an alpha particle with 4 and 2. So this here is alpha radiation. There you go. That's alpha radiation. Beta radiation is what we've already seen, where we've got beta decay, and I think I've already called it that. So when you've got a neutron, it goes to a proton. It's beta minus, so we've got beta minus decay, plus VE anti-neutrino. This here is beta radiation. So the thing about Yeah, we've also got gamma radiation, which is what we got when we got annihilation, for example, where we had 2 photons. Gamma is basically just high energy photons with a really high frequency. That's what gamma is. And we can calculate the frequency through E equals HF, and if it's got high enough energy, H is a constant, therefore F must increase with E, and as we know, gamma is at the top of the EM spectrum. It's going to have the highest frequency, so we're going to need a high frequency for gamma radiation. So let's start off with alpha. An alpha particle is highly ionizing, but it's very poorly penetrating. In other words, it can ionize something really well, but it can't even pass through air. It can only pass through like a few centimeters of air, or it can't pass through paper, for example, but it will ionize things and radiate things as long as it's within a very short distance away. Then got beta decay. Now beta, it's sort of in between the two. We've got more penetrating power, but we've got less ionization. And then we've got gamma radiation, which basically has an infinite penetrating power, but it's very, very poorly ionizing. It doesn't do much. Yeah. So due to the penetrating power being so high, we can't really stop it. I mean, you can reduce it. You can reduce the intensity of gamma radiation through lead and concrete, but you're never going to get rid of it. It's always there because of the penetrating power of it. So that's radiation. Different kinds of radiation. I mean, I could talk about photoelectric effects. Sort of particles. So we've got a particle called a photon. Photon has particle properties, but then it also has wave-like properties. Now, the reason it has these two properties, we don't really know, but we know what causes them to have the properties and or how we read the properties. And for wave-like properties, we've got things like double slit, which was done by Thomas Young. We've got particle properties. We have the photoelectric effect. Which was done by Einstein, I believe. So the photoelectric effect is where we shine a light onto a metal surface and we essentially see electrons emitted from the surface. And the reason we think we know that it's a particle property is because increasing the intensity of the light and increasing the energy of the frequency of the photon. That's it. So we've got E equals HF. Right. And if we increase the frequency of the photons, So if we go further down the EM spectrum, we're going to have more energy. And if it were a wave, you'd expect it to essentially emit more electrons from the surface, but it's not that case. It's a case of high frequency means that it has a higher energy, therefore the electrons that are emitted have a higher kinetic energy, and we're more likely to overcome the work function of that metal. Now the work function is the energy required in joules to sort of emit the photon from the surface of the metal. So as I said previously, an increase in frequency will cause an increase in energy through E equals hf, where h is Planck's constant. We then know that if energy is increasing, then of course the total kinetic energy is going to increase. But then how do we increase the amount of electrons? We do that by increasing intensity. So as intensity increases, we get essentially more particle forms of photons incident on the metal. Therefore, we get more electrons emitted. It's all about that frequency, and the fact that if we have a wave, and if we increase the frequency of the wave, then you'd expect to see more electrons emitted, right? But it doesn't. It behaves like a particle in this scenario. So as frequency increases, energy increases, and again, if it were a wave, then we would see an increase in the amount of electrons emitted if we increased the frequency of the wave. But obviously that just proves that it's a particle in this scenario, of course. But it's important to express the Joule-like nature of the photon. So, I mean, technically, a photon is neither. Well, we can't prove that it is either a wave or a particle, but it just behaves in that way. So we now have the double slit experiment. This is where we see diffraction of a photon. We have two slits, and we have a source. This is one source of light. Source of light, and then we get essentially we just get the light interfering with each other, and then we have a screen over here, and we get a pattern that has equally spaced fringe spacing or fringe width. So that's what we see on the screen here, and that's essentially just the light interfering with itself. And if it were to be a particle property, then we'd expect to, it's going through there, it's going through there. So you'd expect to just see dots there and dots there, but we don't. We see a diffraction pattern through constructive and destructive interference of the waves. So that just proves a photon to also have wave-like properties in some scenarios. Right. Cool. I think that's most of particles covered, really. That's what we got. I don't think there's much more, to be honest. But yeah. Thanks for watching.